Hello, everyone. I'm very happy to be here today. This is my first KubeCon. And it turns out the best way to attend KubeCon is to actually speak at KubeCon. So those of you on YouTube, if you want to join, if you want to attend, submit proposals, and maybe, just maybe, you will get in. So the title of today's talk is Fuzzing for Stability. My name is Jakub. I'm working at AlphaSense as a cloud platform tech lead. And I'm very grateful to AlphaSense for sponsoring the tickets, for sponsoring the hotel room, and also enforcing the kind of culture that allows you to do this kind of work. And I'm very lucky to be joined by around 10 of my coworkers right here. They are supporting me. It's very nice of them. And a bit more about me. I come from Europe. I have a dual nationality, so I'm both the citizen of Poland and a citizen of Sweden. And for those of you in India that maybe never were in Europe or you don't know much about the Polish or Swedish culture, an interesting thing common amongst those two countries is that we have a pretty interesting alphabet. So you can see the example of a Polish bison, the żubr. You can see the cute Z with the dot. And the Swedish elge, which is the word for the moose, has 2 dots over the A. So my day job is around cloud orchestration, cloud APIs, but some of my other interests include compilers, cloud computing, cybersecurity, and performance optimization. So this talk will include all of those topics. And what I want you to get out of this talk is learn more about the CVE process, how does it happen, learn what fuzzing is and how can you use it for various means, and also, hopefully, you can try to contribute yourself. So first things first, CVE 2024-26147. This is a high severity denial of service vulnerability I identified in February. And this was found in Helm. How many of you know what Helm is? Can you raise your hands? Quite many. This is a very popular mature core cloud software. It's quite not a common occurrence to find vulnerabilities, but apparently it still can happen. So when I reported this, it was actually 2 different vulnerabilities. And I reported this at 2 different points in time. But since the core cause was the same, the Helm maintainers decided to bundle it together and release a single CVE. So the first part of the vulnerability affected the repository system in Helm. So Helm allows you to add repositories. And every repository comes with a metadata file called index YAML that encodes some additional data. And on the left side, you see the vanilla, normal, healthy metadata file. And on the right side, you can see the malicious version of it that is a bit smaller. So the core issue here was that the metadata was missing. And that led to a nil pointer dereference that causes program termination. And this is the fix, 4 lines. So basically, we check if the metadata is nil. If it's nil, we zero initialize it. This is the second part of the vulnerability, affecting the plugin subsystem. Again, similar story. On the left side, we have a healthy metadata for a plugin. And on the right side, we have a malicious version of it. And you are right, you are correct. It's an empty file. So an empty file was enough to trigger this. Yes, there is no white space there. And this was the fix. Again, 4 lines. We check if the metadata is nil. If it's nil, we zero initialize it. And the core issue was that metadata can be a pointer, and we dereference this pointer without checking first if it's nil. And for those of you that have never seen a CVE get patched in an open source software, typically when it happens, when a vulnerability gets fixed, the commit is very innocent. It doesn't announce the vulnerability. It tries to be as low-key as possible. So if you see a commit that looks kind of weird, a maintainer sends some weird, not described commit, and you're wondering what's happening, it's very likely they're patching a security vulnerability. And in this case, you can see the Helm maintainer sent a commit called some fixes, okay? So that was the entire story. Why is that? Well, if you think about it, the reason is quite simple. If this is open source software, before you release the CVE, you need to release the new version, right? You need to build it, you need to release it, and only then can you actually publish the CVE, right? Because if you don't do that, then the malicious actors have a window of opportunity to exploit this. So I was curious what kind of impact this had in community, and I checked around 2 weeks ago. When I took this screenshot, there was around 750 pull requests mentioning the CVE in various projects from Console.KIS, Operator SDK, Cert Manager, Tri-V, Argo CD, Flux CD, so there were hundreds of projects affected. There were some commercial products impacted. So Google released 2 patches for GKE on-prem and classified this as a high-severity container vulnerability. And then Red Hat released several RHCAs, including an RHCA for OpenShift, so it was also quite a real vulnerability. So what I will try to do now is actually demonstrate it. And I actually hope things fail, because this demo is supposed to trigger a failure. So let's see. So as luck has it, I actually prepared a malicious Helm repository. And I do have an older pre-patch version of Helm. So I will try to use that repository now. And we see a beautiful stack trace, a nil pointer dereference. And you might think to yourself, so what? Right? This is a CLI tool. I can just run another command, for example, Helm version, right? It still works. Well, the thing is that Helm is both the CLI project, but it is also the SDK, okay? The library, and hundreds of projects embedded. So projects like Argo CD, Flux CD, what have you. So if you are able to trick that program into interacting with this malicious repository, it would actually explode, it would crash, and you could trigger a denial of service, which I think was kind of cool. The second part of the vulnerability, I think, is much more interesting to me. So Helm allows you to install custom plugins, right? So I prepared a malicious plugin, and if you want to try it out on your machine, it's in my Git repo. So let's see what happens when I try to install it. We get a nil pointer dereference, right? Same story. Like, what's different here? It's boring. Like, who uses plugins anyway? Well, let's see what happens when I try to list releases. It panics again, right? What happens if I try to invoke the simplest of all Helm commands, Helm version, that basically just prints a string to the CLI, right? OK, again, we get a SIGZEV, and it turns out that even though Helm panicked during installation, the malicious plugin metadata was inserted into your file system. And what Helm does on every single invocation, and it happens very fast so you don't notice, but it happens every time, is it will look over the local file system, load the plugin into memory, try to parse it, and then it encounters that nil pointer dereference, and it blocks all subsequent actions. So if you were able to trick anyone into installing this, you could break their Helm, which was kind of interesting. But how do you think I found this? A, did I mess up copy-pasting YAML? Was there a typo somewhere? Or B? A? Reading the code? Maybe I called a friend that knows this kind of stuff. Manish usually knows this kind of stuff. Actually, it was D. No one guessed. Bad luck. This was a result of a targeted fuzzing effort against Helm. But before that, really, like, this vulnerability is cool. It's really nice to have a CVE in a very popular cloud software, right? Like, it's a kind of bragging point, but really this wasn't a very impactful vulnerability. There wasn't a big there wasn't a big economical damage. You couldn't really do much with it. But let's look at some other vulnerabilities. For example, Heartbleed. How many of you heard about Heartbleed? Right, very famous vulnerability, published around 10 years ago. How about Shell Shock? A few of them, yes. Finally, a more recent example, WannaCry, Eternal Blue. Very big, famous attack, ransomware. Many hospitals were shut down, airports were shut down, billions of dollars in damage. Is there anything else common amongst them besides the economical impact? Why am I talking about them? Well, it turns out that all of them were found using fuzzing, and this is a bit of a secret in the industry. It's not often talked about, but many high-severity, real vulnerabilities get discovered using fuzzers, okay? And yeah, the WannaCry was a result of someone reverse engineering malware created by NSA, which is kind of interesting. I think what goes around comes around. What is fuzzing? How many of you know what fuzzing is? A few people. So it's really a simple technique. What you do when you fuzz software is you take your program, parts of your program, perhaps a single function, and you feed it with random data, okay? And you do it very fast. Some fuzzers, like the Go standard library fuzzer I used to find the CVE in Helm, are a bit smarter than that. Not only will they generate data, not only will they execute your function, but they are also aware how your program executes. So they can be even more smarter about how they generate data. But before that, a little workshop. So I prepared 2 problems. The first one is easy. The second one is hard. And maybe we can figure them out together. So let's look at the easy level. I know not all of you are Go developers. Probably not all of you are programmers. But maybe there is some in the audience. So my question to you is, what value of n makes this program panic?
Anything negative or beyond the length of the string.
And what is the length of the string?
Looks like 3, so anything beyond that 4, 5.
Well, it turns out 3 would also make it panic, but almost there, almost there. So why is that? Because in Go, like in many programming languages, we count indices from 0. So A is 0, B is 1, C is 2. If you tell it to print character at position 3, you are technically telling it to print position 4, okay? And that memory doesn't exist. So Go, being the memory-safe language it is, it exits. It protects you against those kind of failures. So this was kind of easy. Humans can figure this stuff out. But then let's look at this one. So this code is from Go 117, time parsing library, official standard library function. Can you tell me the string that makes this one panic? Anyone? No? Well, obviously, it's x85, x85. Like, you can see it. Well, apparently, it's very hard for humans to figure this out. But if you take the Go standard library fuzzer, it will find this in 1 second, or less than 1 second. So it's a very powerful technique, in many ways superior to humans. And it used to be the case that fuzzing was a very arcane technology. It was very hard to use. It required you to have a lot of domain knowledge. But Go is the first language that has it as a first-class citizen of its testing library. So fuzzing this code is as simple as writing those 5 lines and running it. And it's very simple. OK, so I will do some fuzzing. And we'll start with the second case. I prepared a target. Yes, so this is the target for the plugin part. And you can see the screen is cooperating. The title of the talk is Fuzzing, and the screen is very fuzzy, so it's not a bug, it's a feature. I ran the fuzzer, it found the failing input. It stopped, and what it did is it saved the malicious input into the local file system, so you can actually inspect it, take it, write it up, send it to maintainers. They will acknowledge it and release a fix, right? Very simple. It wasn't hard. It took me 1 second, right? Now the second part is a bit trickier because fuzzing is probabilistic. It's random. And sometimes the functions are very complex. So it's not very simple for it to find some cases, like the case of the repo index. So if I were to run this from 0 on my MacBook, it takes approximately 3 hours, okay? So in the interest of time, I will spare you that, okay? We will not wait here. So I prepared faster fuzz test version of it, which basically encodes the failing input. So you can again see when I run this one, it will explode. Hopefully, it should fail, right? Yes, we get the stack trace. So that's basically it. How simple was it? Like, did I have to do a lot of stuff? No, I just used the tech, right? It's not that hard. So what's in it for you? Well, there is 3 main paths. So the first one, obviously, you can fuzz your internal projects, right? And fuzzing isn't limited to cloud-native software, and it isn't limited to Go, okay? There are fuzzers for all different kinds of languages. So you can integrate them in your CI, run them on every commit, and given the random nature of fuzzers, you have a chance of uncovering bugs and security issues. The second path, which is also interesting, is to fuzz open source software, like I did with Helm, okay? So there is likely hundreds of undiscovered bugs in C and CF software that are waiting to be found in projects like Helm, Kubernetes, Docker, Crossplane, yada, yada. You can fuzz those projects. If you find something, report it to maintainers, and you can help the ecosystem, right? And the third path, which is the most interesting to me, is to improve the base fuzzing technology. But before we do that, let's maybe explain a bit how fuzzing actually works in Go. So when I ask you, how does a program look like? What do you imagine? You imagine lines of code, right? Like that's what pops into your mind. If you work with compilers or you had a compiler engineering course in university, this is yet another representation of the very same program using the SSA, static single assignment, CFG control flow graph. So you can see the basic blocks in the SSA form that show the control flow of the function. And if you squint hard and kind of look sideways, this kind of looks like a banana, okay? I want you to remember that because it's important. So that was a simple function. The control flow can get very complex. We have different kinds of blocks. We have, here at the top, we have the B1, which is our starting block, a conditional block. Then we have more conditional blocks like B6, B10, B14, B18, B22. Then we have ret blocks, which return the execution to the caller. And we have the very interesting block, B20, which a panic compiles to. This is an abnormal program termination. And like I said, the control flow can get very complex. So this is another function. It's not very complex. There are functions that are 100 times more complex, okay? And because we have conditional blocks, because we can have loops, what ends up happening is if you were to try to trace the amount of unique paths your execution can take in this program, it's over 1,000 or maybe even over 2,000, okay? And if you try to do that by hand, it would take you ages. but fuzzers can do that very quickly. So let's do some fuzzing, OK? Let's do some manual fuzzing. So I prepared a toy function. And we will keep giving it some inputs and see what happens. So first input, not 5 letters. It's a string. What happens? On line 4, we check if the length of the string is 5. If it's not, we go to line 22. And then in the SSA CFG form, you basically go from the B1 block to B2 block, OK? We didn't get very far. Let's try more. Bliss. OK, this time, the string is 5 characters long, right? So we got a slightly further. But then we fail on this line. The first character is in B, is in C, so we exit, right? And in the CFG form, we went from B1 to B6 to B5. And then if we continue doing this, charm, we get 4 blocks. Crisp, we get 5 blocks. Crave, we get 6 blocks. Crush, we didn't get B20. Why didn't we get B20? Yes, because for your CPU, lowercase h is a different number than uppercase h. For humans, it's easy to see, OK, it's the same one. But CPUs operate on numbers, and those are 2 different values. So you don't take this branch, or actually you take this branch. But then let's see what happens if we run the crush with lowercase h. We reach block B20, right? And then we have a beautiful explosion. We found a vulnerability in our awesome function, right? So that's how fuzzing works. If you were to fuzz a function by hand, that's how it works. A bit more low-level details. So a little bit of trivia. The Go compiler and Shrek are both like onions. They have layers. So on the left side, you have the vanilla Go code, OK? And then you have the optimization onion that progressively improves the quality of your code, makes it smaller, makes it faster. And at the end, you end up with raw assembly that your CPU will actually execute. Why am I talking about this? Well, it turns out that a big trick in the Go fuzzer is that it is smart, OK? So when you compile that function the typical way, it looks like the one on the left. But when you fuzz it, the Go compiler actually compiles it differently. So it will instrument the basic blocks. It will insert transition blocks between the other blocks. And then our banana tree looks more like a Christmas tree, OK? And I will explain why do we get, some of you might think, why are we getting more conditionals in this instrumented version? I will explain that. This is yet another view. On the left side, you have the raw, vanilla compiled version of the function. Beautiful control flow. On the right side, the highlighted parts are the coverage counters. So we load values from memory, we check them, we increment them. And that's how it works. That's how Go knows whether it's covering new code or not. So how does this all work? Well, the first phase is to instrument the code, right? Insert the coverage trackers. The second part is about bringing up the entire system. So at its core, you have the main process that's kind of like the Kubernetes API server. It manages all the elements of the system. Then you have something with a really cool name, mutator, that integrates a very fast random number generator and generates huge amounts of data, OK? And then what we do is we spin up several instances of your function to fuzz in parallel, right? The mutator will generate data. We will feed it to the instances of your program. They will get executed. And the worker will look at the vector describing the execution path, report it back, and we check whether this was a new path or not. OK? This is very important. We are only interested in paths that are actually new. if we've seen this path, we discard it, okay, because it's not very useful to us. And you basically keep doing this, okay? Like that's how it works. You keep doing this until you get a crash. And that's it. That's the whole story. It isn't really rocket science. A bit more detail. This is an entire set of all the byte slice and string mutators the Go fuzzer implements. Those are simple transformations. And they have to be simple because the fuzzer's quality is very proportional to its speed of execution. So the faster you can generate new inputs, the faster you can execute them, the more paths you can discover, okay? So we have some very simple transformations: removal of bytes, insertion of random bytes, swapping bytes. And this is a sample mutation, removal of bytes. So let's say we have this candidate here. We apply the remove mutator, and we end up with our crusher. Insertion, again, we have CR, we insert random bytes, we end up with our crusher. Swapping of random bytes, we end up with our crusher. So why am I talking about this? When the Go fuzzer was released, it was a really big news. There was a lot of buzz around this. People were very excited. But if you look over the last year, there's only really a single person working on it. And this is an open source project. You can contribute, okay? And you might think, how do I contribute to something as arcane as a fuzzer, okay? That sounds hard. Well, you do it the same way you do it for any other kind of software. So you fix bugs, you add new features, or something that I'm most interested in, optimize performance. So it turns out I did some work around this. And remember when I said that our banana tree becomes a Christmas tree? The reason is that the Go fuzzer implements the never zero strategy from the AFL fuzzer, which basically means when we count the amount of times a block got executed, we increment it. But if we are about to overflow, which is go from 255 to 0, we don't go to 0, we go to 1. And that results in control flow, okay? And for those of you that care about performance optimization, CPUs really hate control flow, okay? They have this part called branch predictor, and it's really awesome about guessing where the program will go. But in general, it's still much nicer to try to use branchless algorithms. So in this case, I implemented the function at the bottom. I swapped the part in the compiler that instruments the fuzz targets and implemented a branchless version of it. And the benefit of it is that our banana tree remains the banana tree, okay, so that's really nice. And you might think, okay, the tree is much simpler, like how big of an impact did it have? Well, it turns out only 2% performance gain, not much. It was very hard to implement this. You have to have the context of the compiler. So it was, I mean, it's nice that it's 2% faster, because what does it mean? Now if you run the fuzzer for the same amount of time, it's 2% more likely to uncover new code paths, new vulnerabilities. But let's look at something simpler. So remember when I said when the worker executes an input, after that execution, we look at the coverage vector, and we report it back. And it turns out the Google engineer that implemented this did a great job and coarsened those coverage trackers. So instead of reporting the actual number of executions for every block, we round down to the nearest power of 2. And that beautiful bitwise trick, those 4 lines actually do that. Like if you run any byte through this, you will end up with a nearest power of 2, okay? So I looked at this, and I thought to myself, you know, this is a very hot path. It executes every time you feed it an input, so it runs very often. The coverage vector can be very long also. We can have many blocks. But I looked at this, and I thought, you know, when you're in middle school, and the teacher asks you how much is 5 times 9, Were you counting on your fingers? I know some of you did, but most of us didn't. What did we do? We remembered, right? We remembered. So it turns out, what if we actually pre-compute all the answers once ahead of time on initialization, and then instead of doing this awesome, beautiful bitwise trick, let's just look up the answer. So 17 should be 16, 33 should be 32, 9 should be 8, yada, yada. Much simpler optimization. You didn't have to touch the compiler. There was no SSA, none of that stuff. Well, it turns out that's an 18% performance gain in the fuzzer, which is nice because it means if we combine those two optimizations, now we will have 20% higher chance of uncovering new code paths. And since this is a foundational software, hundreds of people rely on it. So if you are able to improve base technology, you can improve all the work done by all those people who actually use it. So I think it's a really good karma. If you want to do something good for the world, this is one way to do it. And to finalize, I just want to reiterate that fuzzing is absolutely not limited to Go and cloud-native software. There are fuzzers for all kinds of languages: Java, Python, JavaScript, C++, C#. You can fuzz all kinds of software. Customer-facing APIs, mission-critical systems, business applications, like really anything that takes inputs, okay? Like you can, if it accepts something, you can send something, right? And you can find many different types of issues: SQL injection vulnerabilities, denial of service vulnerabilities of different kinds. You can also apply a very interesting technique called differential fuzzing. So let's imagine you are implementing a compression algorithm, a lossless compression algorithm. You could make the fuzzer generate inputs, compress them using your compressor, then decompress them using your decompressor, and what should you see? The input and output should match. If they don't, it means there is a bug, there's a logic bug in your function. So this is all I had for you today. Feel free to reach out on LinkedIn. You can email me if you have any questions. And try it out. Like the code base is a few thousand lines of code. You can spend a few weeks trying to understand it. It's likely that you might find ways to contribute. And thank you. Any questions? I was expecting roasting, like very hard questions, to come like, oh, what about that fuzzer? Like, no one has any of those? Oh, someone's coming.
Hello.
Hi.
Great talk, first of all.
Thank you.
So my question is regarding, you mentioned we can fuzz customer-facing APIs as well.
Yes.
Right, so I'm thinking JSON or any kind of structured input where some keys have to have certain values. So are there predicates that we can give to fuzzers that I want
yes,
this
it's
structure?
up to you to define the predicate. In the case of Go fuzzer, if you don't have a predicate, it will fail on crashes, obviously. But you can have additional predicates.
Okay, so I can nest predicates as well if I want to make one.
It's basically a program. Like you can make it as long as you want, Okay. Yeah.
Thank you.
Any more questions? Please don't be shy. Yes?
Are there any CI tools for fuzzing?
Yes, you can use GitHub Actions or Bitbucket and just use, you can have the Go CLI. If you have the fuzz test defined, you can just run go test fuzz. You can have a simple pipeline that does that. And then what you can do is you can define the amount of time it's supposed to execute for. Okay, so you can say, please fuzz this for 1 minute on every commit. And given the random probabilistic nature of fuzzers, it will have a chance of uncovering new code paths. A potential optimization you can do is you can, because when it finds interesting inputs, it will save them to the file system, right? But if you run it in CI, it will lose them on every execution. So you can try to implement caching for it, you know. There's a little bit of, you have to kind of integrate it with CI, like it requires a bit of.
Like, as you mentioned, a memory function itself. So like, if every commit is a single line change or 2 line change. So can I have a sort of CI tool that already have a memory function and only does the fuzzing for the change implemented?
You can do that, but the thing is, like, you know, some functions, if you were to fuzz them, it will take, you know, a year to find the buggy input. It's a very probabilistic process. So it's not like, okay, I will fuzz it for 1 minute and I will, you know, find all the bugs. You have a chance of finding something. Like, and sometimes there are areas of your code that exist, the compiler emitted it, but you will never reach them, no matter what kind of input you pass. They exist, but you will not be able to ever reach them in any way. So what you can do in that case is you can save all the interesting inputs you got and run them with something that has coverage tracking, like a unit test. You can have a unit test that sources all the inputs, executes them, and then you can see which lines were covered. Okay, if you see, okay, I covered all the lines, there's probably nothing to find here, then probably you're safe. But the search space in some functions, especially the ones that accept byte slices or strings of unlimited length, like it's infinite. Like you can never really execute for all the, yes.
Do you have strategies that you've seen projects doing where they just have some, maybe some, what do you call it, some prefixes that are for sure to be tested and something?
So I didn't talk about it, but this is very good to do, is you can add the seed corpus. So when you start fuzzing, you can show the fuzzer examples of valid inputs. Okay, it will try to mangle them, and it's much more likely it will find like real code paths. Because if you don't do that, it will start from zero. Like it will start with an empty string, random characters, and then imagine you have to start passing valid Helm chart metadata. It will take you like 3 hours, you know, for the fuzzer to kind of find that structure. So it's good to provide a high-quality seed corpus that can significantly speed it up. Yes. Yes?
If you have a nested class structure where your main class is delegating the APIs to the next other classes, so what is the best practice to start fuzzing from the nth depth or from the top?
That's a good question. I probably would have to think about it to not mislead you. Well, I think it depends how do you actually consume that class. Like, because you know you fuzz things that actually you can feed inputs into. Like that's what you fuzz, okay? APIs, file system, something that you can send data over. Like you take that, you feed data, and then you wait till it explodes. So if you know, depending how your code actually integrates there, like fuzz that, okay? Yes?
So you said to integrate it into CI, right?
Yes?
And then at the same time, we're also talking about running it for 3 hours. So how would you balance out both of those things?
Because you can fuzz outside of CI, and that's why I did. And the question was that I mentioned that you can run in CI, but I also mentioned that you can run for 3 hours. And the way I did it is I basically made my computer run for 3 hours, and it found it. But there are projects. I think there is one called OSS Fuzz. that handle they fuzz continuously using huge amounts of machines. And I think Project Zero from Google also does that. Like they have a lot of hardware and they fuzz popular programs and find bugs in Google Chrome and all kinds of software. So the more hardware you can throw at it, the better, okay? Like, it's kind of nice. You set it up and then you wait until it finds something. You can go somewhere. Yes?
In cases where you find a problematic input, but maybe the issue happened already, like you found a longer input, say 10 characters or 11, but maybe the 6th was the one that caused the pain. So have you ever had an experience where you have to reverse it?
Yes, and there is a part of the fuzzer, I did not mention it. There is a part that handles what's called minimization. So there is a step where you find a crasher, you actually try to make it as short as possible. So you remove random characters, you run it again, and you see, am I still triggering the same code path? Yes, okay. Can I make it smaller? And then you continuously do that until you cannot minimize it more. Yes, there is a minimization step. Though it isn't perfect, yes. Yes?
The Helm CVE you found, so
Yes?
was some minimization step in that step?
So yeah, I copy-pasted the input that the fuzzer found, and then the maintainer was like, oh, it can be a smaller one. So it isn't perfect, you know? It isn't perfect. Sometimes there is too much, too many characters. And that's like an area you can contribute to. Like maybe there's a better way to do minimization, you know, like, yeah. Yes?
So you already covered that it takes a lot of time. It requires high quality seeds, and you might have to be probably aware about what kind of predicates you want to run. And because of that, it may go over a budget, and every team has a budget. So my question is, how can I learn more about best practices of creating a good seed and making sure my predicates are good, but they are not too minimized that I would never actually go and break my code?
Well, there is likely, you can get a lot of benefit just from base fuzzing, like not elaborate fuzzing. If you start fuzzing basic code, it's very likely it will find issues, you know? So
Good resources where we can learn more about fuzzing and get the team ready for that as well.
I think the official documentation is quite good. Like if you read through that, it's quite good. I think there are some tutorials on YouTube also. A few other talks about fuzzing also. So there are resources. And once you write your first fuzz test and run it, like it clicks. Okay, it's quite nice. So. Okay, I think we are done, right? What time is it now? 28. No more questions? Thank you. No, you had yes? Yes?
Basically, you're talking about us testing the code.
Yes?
How do I do it in case of containers or the infrastructure?
That's also code, you know, like you can, if it runs on a machine, it's code. Like you can find ways of fuzzing APIs for containers, for example. There is something called black box fuzzing, which doesn't have this instrumentation step. So you can fuzz using the black box technique where you just send data and like see what happens, like, but it's much slower, you know, like if you don't have this instrumentation, if you don't integrate the fuzzer with your source code, it's significantly slower. But sometimes it's the only way, right? Like if maybe there isn't a better way. Okay, thank you for today.